Hello. In this video, we're going to talk about your next homework assignment using Twitter and Postgres in parallel. I'm going to share my screen here. And so recall that our last homework assignment was on just combining Twitter and Postgres, and we were investigating the normalized versus the denormalized databases and how to just load data into these databases in a sequential manner using this sort of artificial testdata.zip file right here. Our next assignment, the Twitter Postgres parallel repository, is going to build off of this previous assignment by doing things in parallel. In this case, you can see there are many test cases here, 6 test cases in total, and 3 of them are already passing. These 3 green test cases right here are corresponding to sequential insert operations and actually contain the answers or my solutions to the previous homework assignment. One of the things we talked about in the previous homework assignment is that your implementation of the insertion process into the normalized database was not optimal because it was not batched. It didn't do the batch insert operations. So it was inserting only 1 tweet at a time rather than say 1,000 tweets at a time. And it turns out that in Postgres, and actually all database systems, it's just as efficient to insert 1,000 things at once as it is to insert only one thing at once. And so the batch operation here, I've implemented it for you, and this is the most correct way to insert things into a normalized database system. We'll go over to the terminal here in just a little bit, and we'll see just how much faster the batch system actually is. But again, the main purpose of this assignment, I'm providing you all the code for these sequential things. The main purpose of this assignment is to explore for the parallel operations, how to make them parallel, and what you're going to have to change in the code in order to do that, both at the shell level, terminal level, and at the Python level. Okay, so let's, the setup for this problem or for this homework is basically the same as all of the other ones. The sequential data loading section here has just some tips on doing the sequential data loading and is essentially the same as your previous assignment. I'm just going to walk through these steps here though in the terminal so that we can see exactly what's going on. So I'm going to switch my screens here to the terminal. I am in my Twitter Postgres parallel repository right now. I've already cloned it and gotten everything set up. If I run Docker PS, you can see that I have nothing running right now. Let's do a Docker PS-A. I do have some of these things running though. So using my Docker skills like that, Docker PS-A. Now we have nothing running at all. Again, what this Docker or what the -A flag does is it lists all the Docker containers that exist but are not currently running. So they've just been stopped but have not been deleted. The -Q flag right here says that instead of instead of listing all the information about the containers, list only the IDs of each of these containers, 1 per line. And then we use the command substitution right here to pass that into the docker rm command, deleting all of those Docker containers. And I probably didn't need to do this, but it's just a nice thing to do to clean up my Docker systems, make sure I'm not using more disk space or memory or compute resources I need to. I'm also going to do Docker volume prune right now, just to make sure that if I have any volumes related to this project, that they are taken away and not eating up disk space for us. Yeah, I think that gets us into a good clean state now. We'll do a Docker compose up -d here. And I'm getting these bind error messages like we got before because in our Docker compose file, I have to set my port numbers to the appropriate values. So let's go ahead and do that. Docker compose 14GG, take me to this line, F1, A to append 5432 escape colon W. And I'll just do that to all of these 5432. And now there are 3 services inside of our Docker Compose file instead of just 2. This additional service down here for the normalized batch system. To start with, the normalized batch system is going to have the same schema as the batch service does. But we're going to see that this schema is going to run into deadlock issues when we start parallelizing the insertions. And so we'll have to change the schema in order to remove those deadlocks. And that'll be a real pain in the butt and the main challenge of this particular assignment. Okay, so I've changed all of the port numbers here just by adding the 5432 for the Postgres number at the end. Again, everybody will need to use a different port number for your systems here. We'll save that, and then we can bring up our Docker Compose. Ooh, let's see. True well board. Listen on. Oh, bind address already in use. So then we got it's still in use. 14gg find to R3. Let's go to the next. Find to R3, and the very last one. Find to R3. I guess I didn't mention this when I was in the Docker Compose before, but we do have 3 volumes, one for each of these services down here that we'll be using. Save that, come down here, up arrow, rerun. And things are looking good now. Okay, so now we're in a state where we can start talking about what's going on in these databases and how to insert into them. Let's go ahead and quit out of here, run ls, see what's inside of my repository here. I've got the same SQL folder and expected folder and check answers as we've had in our previous assignment. If I type ls SQL like this, we have the same SQL problems, same SQL statements in here. Then SQL / just take a look at the simple one right here. And so just counting from the number of tweets. And again, just like the previous homework assignment, the goal here is not for you to write the SQL that is doing the select statements. Instead, the goal is for you to insert the data into the database in a correct way so that these select statements return the correct answers. And those correct answers are, again, in the expected folder. And there's no nothing unexpected, I think, about that. One thing that's a little bit different from the previous assignment is this data folder. Now, if we look in the data folder, there are 10 different files right here corresponding to 10 different days of Twitter data. And these are real tweets taken from these 10 days right here. But if we use our disk usage command, du-h d data like that, we can see how much disk space this is actually taking up. And we can see that it's only 53 megabytes of disk space. It's only about 5 megabytes per file. If I use my unzip-p command on one of these files, so data geo twitter 0101. Zip, again, what the unzip-p command is going to do is it's going to print the contents of the zip file to standard out to the screen. But I'll pipe that to wc-l just so we can count the number of tweets in one of these files. And we can see there's 10,000 tweets in this file. So we're still not working with the full data set of tweets, but we're getting closer. Now we have, instead of just one zip file that we're working with 10 different zip files, and we're going to insert all 10 of these zip files into our database in parallel at the same time. I've just shrunk the zip files down here using only the first 10,000 tweets from each day so that, well, for 2 reasons. The first is so that you can get faster feedback on whether your implementations are correct or incorrect, that it'll only take a minute or 10 seconds-ish for certain operations to insert these. But That's the first reason you get the faster feedback. The second reason is that I still want to be using GitHub Actions to check our answers and verify our results here that you're inserting correctly. And again, whenever we're using GitHub Actions, we can't use these multi-gigabyte or multi-terabyte data sets because GitHub Actions doesn't let us do that much compute for free. So it's very common to use just small truncated versions of these large data sets to test things out. Okay, so we have 10,000 tweets per file, 10 files, 100,000 tweets. And let's take a look at what else we have in here. This load tweets sequential.sh file. This is basically the solution to your, well, this combined with the load tweets.py is the solution to your previous homework assignment. Let's go ahead and take a look at that load tweets underscore sequential.sh here. And you can see that we have this load denormalized, load normalized, and then load normalized batch down here. And it's got the right code in order to actually do this. The URLs here, though, are incorrect at the moment. They're still using the 1, 2, 3 ports and not the new port numbers that I have assigned to my Docker Compose file. So let's go ahead and fix that. Tab E, open up my Docker Compose.yaml in a new tab just so I can remind myself what are the port numbers that I did. And so I added 5433 to the Lambda server port. Again, the thing to the left is always the thing closest to you. The thing to the right is the thing farthest away from you. And in this case, the Lambda server is the thing closest to us, and the container is the thing farthest away from us. 5432 is the port that Postgres listens on inside of containers, and we're mapping that port to this port over here on the Lambda server so that our Python files can access these databases and insert the data. So I want 15433, and then I think everything is that same number, 25433 and 35433. Yeah. So GT, switch tabs, and then 9GGF1 to take me to this location right here, A5433. And let's go 16GGF2, A5433. And 23GGF3 semicolon. I had to jump over that Python 3 over there. And I'll just use my dot key to put in those 4 numbers for me without actually typing them out because I don't want to do that. And now this is going to be a correct solution to the load sequential.sh file. It's escape:/w. Save that, come down here, and let's try it out. Make sure that it actually works. So sh load underscore tweets underscore sequential.sh, and let's hit enter. And you can see that I'm actually getting an error message right here. It says time cannot run for blah, blah, blah. What's happening here is that time here is a little bit complicated of a command in the terminal. So time here on line 8, a little bit complicated of a command. And the reason, well, why is it complicated? It's if I type down here in the terminal, which time, well, let's do it this way. Time echo hello world. What the time command does is it actually runs whatever command you put after it, and it tells you how long it takes to run that command. In Bash, our current shell is, our normal working shell is Bash, the born again shell. And in Bash, time is a built-in command, reserved word similar to for or while. And this is the behavior that it has. If I type which time, again, the which command tells me where on the computer that I'm currently working at is the time program running. There's another command called the time command, and this is the standard actually GNU implementation of the time command. This thing up here is special for Bash. This is the standard implementation of time. And if I type time echo hello world like this, you can see I get slightly different looking output down here. It actually contains the same information for the most part, a little bit more information, just a little bit formatted not nicely. But here, when I use the here I'm using the time executable. Here I'm using the built-in time command for bash. So there are two different time commands, and we have to be careful about which one we're using when we want to time our program, because they can do slightly different things. And in this case, up here on lines 8 through 10, I want my time command to be timing the entirety of this for loop right here. We'll just take a look at this for loop, see what it's doing. For file in $files. Here, files is all of the contents of the data folder. The find command right here is very similar to the ls command, find data, lists all of the data files right here. The difference between find and ls is that find is recursive, ls is not recursive. So this find data slash star, that happens to be the same as data slash star. Either one of those would have worked. I just happened to use the find command up here. So that gets us our list of files that we're working with. We're looping over those and running our denormalized insertion command into each one of those files. And I want to time the overall for loop. Because this thing right here is a shell special built-in operation and not an executable, I cannot use the executable time command in order to use it. I must use the bash special time command. The special version of the time command is, again, a bash feature and not a POSIX shell feature. I think this is the first of these bash specific things that we've seen in class probably. And you'll notice up here in my shebang line, I'm specifying right here that this file should be run with bash instead of with a POSIX shell. But if I did that, that's what we've had for most of our other shells. This means run it with the POSIX shell. In the Lambda server, that means dash, the Debian Alchemist shell. I don't remember. But it's fast, dash. So that's why we use it by default. Bash is slower, but more featureful. So in this case, this timing of for loops is something bash specific. And so I need to run this shell script with bash. Notice that the name of my file is still .sh up here. It's customary no matter what shell that you're using to name all of your shell scripts in just .sh. But again, the file outside of the Windows world, file extensions mean nothing. This is just a convention for humans to help us understand what a file is for. So I'll use my up arrow to come back to my previous command that I was running, sh load tweet sequential.sh. The reason why I was getting this error down here, the fundamental reason, is because, where'd it go? The fundamental reason is because I was using the dash shell, or a POSIX compliant, or a specifically POSIX limited shell, a shell that has no features beyond POSIX in order to run this. But I need this feature beyond POSIX. This time of for loops is not something built into POSIX, it's something built into bash. And so if I want to actually run this, the long-winded explanation of saying the fix to this is say bash, then the name of the file like that. And we do that, and you can see now it is loading the denormalized database for us right here. Every one of these inserts that happens, every one of these copy commands is resulting in a new line down here being added. Let's scroll up here. Every one of these lines right here is one of these inside of these for loops being executed. You can see there's 10 of them if you count them, and one for each of those zip files, one for each file in $ files right here. And then the output of our time program right here telling us how long it took. Here we can see that it took 17 seconds overall. The real is the overall wall clock runtime of how long it took to do things. So 17 seconds to insert 100,000 tweets. We're going to see is that the normalized is going to be much slower than that, and the normalized batch will still be slower, but in the tolerable range. It looks like though I was getting some errors in my Python down here. Module not found, SQL alchemy. Let's do a quick pip reinstall SQL alchemy like that, and then I'll be able to rerun my sequential insertion commands. I've already inserted this up here, and because this is the denormalized version of the database, there are no integrity checks. And so if I rerun this again, I'm going to insert the same tweets multiple times. I will just comment out these operations right here so that that doesn't happen, and we don't have to think about the denormalized database, and we'll save ourselves a little bit of time too. Down here, up arrow, rerun this, and okay, now another module not found, scicop G2, scicop G2. There we go, up arrow, enter, and there we go. Now it's doing the insertions here. You can see that, so here are for loops. This is about how long probably your code was taking for the normalized insertions. It's printing out one line here every 1,000 tweets that it's inserting. And so it's taking here, what is this, about 5-ish seconds per tweet, or per 1,000 tweets that it's inserting. Each one of these files that we saw is about 10,000 tweets large. So it'll take us about 50 seconds to insert each file, or 1 minute per file. So it'll be about 10 minutes overall if we sit here and wait for all these things to get inserted. It's not going to be important that all those things are inserted, so I'm going to go ahead and Control C, stop this. And I'll just take a look at, I want us to take a look at the normalized batch service as well. So I'm going to comment out the normalized one right here, and we'll move on to the normalized batch, see what that's going to look like. Up arrow. Again, before I run this down here, the normalized is the main thing that you were implementing in the last homework assignment, but both the normalized and the denormalized were in the last homework assignment. The normalized batch here is something new that, that you did not have before. So up arrow, run that. And now you can see here that each one of these iterations is only taking about a second or so to run. And actually, there's only going to be 10 iterations per file. Each one of these iterations is calling an insert tweets plural function over here instead of insert tweet singular, and the insert tweets plural function is inserting 1,000 tweets at a time. So it's actually inserting 1,000 tweets at a time. We're going faster than we were when we were inserting 1 tweet at a time. It's faster now to insert 1,000 tweets than it is to insert just 1 tweet. The reasons for why it's so much faster to do things in batches are complicated physical reasons about how hard drives are implemented mostly. So that's at least on the Lambda server, the main thing that's going on here, that by inserting all the things into the table at the same time, these HDDs, physical hard drives, sometimes we affectionately call them spinning rust hard drives. The little needle that has to read and write all the positions, it doesn't have to move at all. It can just write all the data in the same location. And it turns out that that's a very fast operation on these spinning rust hard drives. The thing that's slow is actually finding a new location to start writing at. I want to let this run to completion just so we can compare the runtime here of our batch insertion operations to our, or the normalized batch to the denormalized operations. And I think we're almost at the end. Maybe while it's doing this, I will go ahead up here, Tab E. Let's take a look at the well, I'll do it this way, Control Z, LS. So Control Z instead of Control C, Control Z, Zeta sends Vim or whatever you're working on into the background. I do that a lot when I'm inside Vim so that I don't have to close my tabs or whatever my state is inside Vim, but I can get a real quick look at the terminal. And I just wanted to show that there's two Python files right here, the loadtweets.py and the loadtweetsbatch.py. The loadtweetsbatch.py is the one that's being run right now that does the batch insertion operations. And if we take a look at that, tab E loadtweets underscore batch.py, there's a lot of the same code that we had before, like this remove nulls and this get id URLs. But now there's going to be a lot of more complicated code going on in the actual insertion process into the database because we have to group things together into batches. And so I'm not going to explain all of this in detail, but you are going to have to edit this code and you are going to have to figure out what's going on in order to edit this code. Okay, we'll revisit that maybe a little bit later. Actually, yeah, since I'm already up here, here where all these insert operations are going on instead of directly inserting into a database here. So you've seen this code before, building up the information that's going into the database. Instead of actually doing the insertion into the database in this location right here, we're building up lists. So here, this users unhydrated from tweets list contains the all of the information that we were inserting into the database at this location previously. And we will append all of those things into a list and then later on insert them all together at the same time. Here's the tweets list that we're building up and inserting. Rather than calling an insert statement, we're just building this list, and later on there will be an insert statement. I'll do a slash for the insert, and so down here in this function, scroll up to the top for you here, square bracket, underscore insert tweets. What did I just do? The square bracket command in Vim takes you to the next top level definition or previous top level definition. So I use that pretty often to navigate functions. If, for example, I just want to show what the parameters are to that functions. So this underscore insert tweets right here, that's where the insert command was happening at the very end of this function. There's a special helper bulk insert function that inserts stuff into all of these tables right here. And then the inserting into the tweets happens here. Relatively complicated SQL commands going on here. You can see that I'm doing some moderately dangerous things here with related to SQL injection, that I'm creating my SQL values or my SQL commands in a manual way rather than relying on SQL Alchemy to do this for me. That's another one of the downsides of the batch mode insertion, is that there's just not a lot of good tooling for automating this at this point. And so you do have to do these more dangerous operations. In this case, I think everything is safe, but if I were code reviewing things from a junior developer, especially, anytime I see somebody writing SQL code and doing programmatic operations and manipulations on that SQL code, that is a huge red flag for me, and that's like, I will focus my time here on this one line of code, spend an hour reviewing it, making sure that it is a safe thing before I approve it for production usage. Okay, that was a big tangent, but down here, what we were doing is we were running all the sequential insertion code, and I just want to show, okay, it took about 3 minutes right here to do the normalized batch insertion. We said it was going to take about 10 minutes to do the to do it without batch. So this is much faster down here. Still not nearly as fast as the denormalized, but batching things much faster than the normalized version. Okay, So this is the setup of the problem at this point. And now the question is, how do we actually get this parallelism to happen? How do we make things go in parallel? I'm going to switch back over to the README file of the assignment here for a second and just review what we've done and go on to the next step. So the sequential data loading, this is everything that we've talked about. Down here, this note has detailed explanation of the output of the time command. For our purposes, we only are going to care about the elapsed or the real time. It's also called the wall clock time informally. This is the actual amount of runtime that the program elapsed. Is broken down into other things, the user and the system runtimes. The user is the total amount of CPU time that your program actually uses. So when you parallelize things, the amount of CPU time will stay constant or relatively constant. That two different CPUs running for 1 hour counts as 2 CPU hours of user time, but only 1 hour of elapsed time. So the user time is useful for just understanding like what is the total amount of computation that happened, because that will be constant no matter what the actual parallelism level is, how many processors you're using. The system time down here tells us how much time the operating system was actually doing things instead of our code doing things. For the vast majority of normal programming work, this is not an important thing. The operating system will do negligible amounts of works for everything we would do in this class and basically everything I've ever done in my whole life. It's only if you're doing like really weird esoteric things, really digging into the hood of various operating system protocols that this figure becomes meaningful. So for us, it's the user time and the elapsed or the real or the wall clock time. Comparing those and understanding those that matters. When you run this load tweets sequential.sh, we saw that we got a bunch of these runtimes as output. And the instructions here tell us that at the very end of this file, under this submission section, there is a table down here. And my expectation is that you will fill out this table with the runtimes that you get from your sequential and parallel operations runtimes. And there's two purposes of that. One is just so that you can actually see that the parallelism is working, that you're getting should be about a 10 times speed up for everything for each one of these systems. When you're doing the insertions, everything will be 10 times faster with 10 files going in parallel. So double check, make sure you're getting that performance increase. That's the first reason, is just for you so that you can see that. But the second reason is that the test cases on GitHub, these sort of test cases do not work very well for measuring performance-related issues. They're great for just measuring whether the results end up being correct or not correct, but they're not good for benchmarking and making sure that things happen fast. So one way that you can really easily pass all of these failing test cases is by not doing anything in parallel. Then you'll just copying all the sequential code over. And that would pass these test cases, because the only thing these test cases can test for is whether the final result is the same, and not about how fast it took to do it. Also on GitHub Actions, they only give you one CPU, so parallelism doesn't help. But don't do that. If you do that, you will not get credit on the assignment at all, because the assignment's about doing parallelism. So one of the ways that I'll be checking that you've actually done the parallelism correctly is, so I will first of all be making sure that these test cases turn green so that you're getting the right results. But then I'll be looking at the table down here, looking at the runtimes, making sure they're reasonable to check that the parallelism was actually working correctly. Also take a little bit of look at your code just to make sure that it's reasonable, but I'm not going to run it or anything like that. Okay, so that's everything to do for the sequential parts of this code. And now let's talk about the parallel parts. And there's, again, three different three different things that we're going to have to do, one for the denormalized, one for the normalized, one for the normalized batch systems. And it's all under this load tweets parallel.sh that we'll be modifying. So I'm going to come back over here to the terminal for a second, and let's close out of these other windows. I just want to compare the load tweets parallel.sh to load tweets sequential. So the load tweets sequential, I gave this working version of sequential for you. All you had to do was modify the URLs right here. And then I commented these things out just for our debugging purposes. But the load tweets parallel doesn't have any working code inside of it. And you're going to have to implement the parallel loading of all of these systems based on the code in the sequential file using this program called GNU Parallel. This GNU acronym, I've said it a couple of times in class. I forget if I have emphasized, though, how to pronounce it. The cool kids pronounce it GNU, pronouncing the G right here. The mascot of the GNU system is a gnu, the animal, which is spelled the same way, where you don't pronounce the G, but the way that the cool open source developers know who's in our open source club is that we pronounce the GNU project as GNU with a hard G out front. So this is the GNU Parallel program that we will be working with. Parallel is a very widely installed program. It's on the Lambda server. It's on basically every Linux distribution. And it's very easy to get on Macs, and but not. I've never used it on Windows. Windows people aren't the sort of people who would like to use this sort of program generally, so it's probably not easy to get on Windows, but it's definitely possible. It is not the thing I wanted to highlight is that it is not part of the POSIX standard, and so there are systems that it's not supported for, but any Linux system will have this program on it. Come back over here to the documentation here. This is the web page for GNU Parallel. The system here has a lot of things inside of it that we don't need to care about. There's a lot of documentation here, a lot of tutorials going on. You can do a lot of very fancy things with this program, but we're not going to need to do any of those fancy things. I'm going to show you here a one-line sort of command about how to use the Parallel program to make your things run in parallel. So we'll spend the next 5 or so minutes just going over this parallel command. And then after we do that, after we have a solid understanding of parallel, we will come back to the assignment right here and I will fully implement the denormalized loading for you in parallel using GNU Parallel. Okay. In order to understand what this program does, I'll use the terminal window down here, just reset, clear my screen, and let's create a quick temp folder for us to work inside of so that we don't mess around with the project in any way. And I'm going to talk about some things that are not related to the Parallel program, but just setting the stage for us using some of our POSIX terminal commands that we're familiar with. And then I will switch to Parallel and see how it fits into those things. So the first thing I want to do is let's just take a look at the echo command for us. Yeah, that's the one I want. Echo hello world, like this, just print something out to the screen. What I want is something that's going to print on 2 separate lines though, and so I'm adding the \n right here as my new line escape character. You can see though the echo is actually not printing the new line, it's literally printing \n. If you add a -e flag to echo, it causes it to interpret the \n and print things out in multiple lines. So this is just my simple way of getting multiple lines here that I can work with. And we've also seen before that if I use the touch command, I can create files. And then with my command substitution, if I pass this as my command over to the touch command, because there are no quotation marks around this right here, hello and world will be treated as two separate parameters to touch and create two different files. Hit enter, type ls. We can see there's now two different files created here. ls pipe cat, two different files created. Let's go ahead and remove those things. Use rm star to remove those. There's another way, though, that I can pass things to this touch command. So we've seen the command substitution. This is one of our powerful tools for working in the terminal. There's another program, though, for doing this called xargs, and we'll take a look at how that works. Here, I will use this same echo, and then I will pipe that to xargs, and then the touch command. So this whole thing right here, this incantation right here, literally what it's doing, we're outputting hello world to two separate lines, and then with output redirection, piping that into the input of the xargs command. What xargs does is it just takes whatever it receives as input on standard in and passes those as parameters to whatever gets placed right here. So it this whole thing will be equivalent to this right here. I'll hit enter, type ls. We can see we now have the hello world, and it's two separate files that have been passed into the touch command here. xargs uses new lines to separate different parameters from each other, so that's why I need the backslash in right here to separate things. This is all great. But what's happening here when I use this xargs command is that there's actually just one touch program that's being run, and it's being passed two separate parameters. In this case, touch is a very fast running program, so it's fine that it's just creating one program and making it happen sequentially. But the GNU parallel program is a drop-in substitute for the xargs command that makes things automatically run in parallel. So press the up arrow, up arrow, up arrow, replace xargs here with parallel like that, and hit enter, and it gives me the exact same results here. Let's do an rm star, make sure that we have nothing deleted, up arrow, up arrow, up arrow, up arrow, hit enter, and ls, and we see that those two files have been created. The end result of using parallel is exactly the same as the end result of using xargs, which is exactly the same as the end result of using the command substitution. But parallel will make, for each argument that it gets in, for each line that comes in on standard in, so for hello and then for world separately, it will create two different instances of this program over here and run them in parallel. So there we go. Hello world being created. Yeah, this little message up here is a kind of obnoxious thing about parallel, is that it wants you to cite it everywhere. Stupid academic thing. Yeah, so that's how parallel works. Now let's see how we can use that to actually parallelize our PG denormalized insertions. Well, in order to do it, let's take a look over here at what we were doing previously. We had a for loop over here, and what I want to do, let's go ahead, 1, 5, G, G, V, E, down, down, yank, G, T, 8, G, G, P, up arrow, D, D, X down, X, colon, W. There we go. So I just copied over the information from the sequential to the parallel. In order to make this run in parallel, my idea is going to be that each of these for loops, they don't depend on each other in any way. So we'll run all of these for loops at the same time. I'm going to do this. Well, before we get to using GNU parallel, I want to highlight the previous way we've seen for running things in parallel using the ampersand. So I could make all these things run in parallel by putting the ampersand at the end over here. And again, what this means is that all of these things are going to run in the background. We're not going to wait for this process to terminate before we go on to the next line of code. I'll go ahead and escape colon W, save that down here. Bash, not sh, bash, load. Underscore, I'm in the temp folder right here. Control C, cd dot rm-r temp. I don't need you anymore. ls bash load tweets underscore parallel.sh and hit enter. And we're going to see what happens when I use this ampersand up here. Hit enter, and immediately you could see that I was getting the output information or the runtime information printed here. It said that the program, the for loop, ran instantly. That's great. Our parallelism was fantastic, but it's not waiting for these programs right here to finish. It's just waiting for this for loop to finish. And the for loop doesn't wait for these programs. It just says, okay, start, and then go off and do your own thing. And so that's why it runs instantly. So one disadvantage of this ampersand over here is that we can't use the time command to see how long things take to run. Another disadvantage is that you can see down here in all the output that's being printed, it's all being interwoven together. You probably noticed this at some point during your Twitter assignment. And I could use like output redirection and things to try to organize that a little bit better, but it's still, I don't know, it's kind of messy. So let's Control C that. And actually, it looks like some here I accidentally am doing the normalized thing in the denormalized spot. So that's not what I wanted. I will DD that, escape GT over here, and up. This is one I want. Yank GT, paste X. There we go. Yeah, we'll go ahead and just for the sake of completeness, show what that looks like here. And then yeah, printed out the runtimes, and then suddenly all these copies got printed after the end, after they actually ran. So that's not what we want to have happen. This is parallel, but it's not the optimal sort of parallel. For the first reason why it's not optimal is that the time command over here can't time things. It also turns out that when we have many things that we're trying to run in parallel, having them all run at the same time with the ampersand is less efficient than having exactly one run per CPU that we have available. And the parallel program will let us limit the number that are running to exactly the number of CPUs we have available. And so it reduces overhead and is really the best way for doing parallelism. Yeah, so we're not going to use the ampersand here. We're going to use the GNU command, and you have to use that actually in order to pass the test cases as well, because the test cases need to wait for all the inserts to happen. The test cases need to wait for all the inserts to happen before running the select statements. And if we use the ampersand, it's not going to wait. So we have to use the GNU parallel program here. How do we do that? Well, the first thing that we have to do, if we recall, I'm going to put down here Control R, just look at what our syntax for the parallel command is. We need to have just a single command over here to the right-hand side of parallel, a single thing over here to the right-hand side that's going to take as input its the parameter that's going to run in parallel. In this case, it's going to take as input the file that we're going to use. And so let's go :tab E. I'm going to create a helper bash script that will do that for us. So :tab E, I will call this, I think in the README file, I have a suggested name. You don't have to use this suggested name, but we may as well. Load denormalize.sh. :tab E load, undo :tab E load denormalize.sh/bin/sh. Up here, there's going to be a POSIX shell script. And what we're going to do, YYGP down here, we're just going to run that same command that we previously had. Instead of the file right here, we want to run the first argument that's being passed in. I'll just echo $1 here so we can see what $1 is doing. And down here, Control C, sh load _ denormalized. Hello, and hello. Whatever the first parameter is to a shell script gets put in the $1 variable. Whatever the second parameter is gets put in the $2 variable. Just hello world, and so on. So it makes it really easy to access these parameters. And so here, unzip-p $1 means that whatever the file is that gets, the file name that gets passed in here, will unzip-p that, pipe it through our big, long incantation here, and insert it into the database. And so over here, instead of doing this big, long incantation like this, I can change that to something like sh load denormalized. Like that. And actually, it'll work without the double quotation marks in this case because there's no spaces in the file name, but soon there will be spaces. And so it's good to get in the habit of putting the quotation marks around all of your variables when you're using them. Let's escape :W, save that up down here. Let's go ahead and just rerun this, make sure that I don't have any problems going on. I do, it looks like. Done, expected, load tweets parallel.sh. It's because again, I'm using the sh command here instead of the bash command. Bash load tweets parallel.sh. There we go. Can't open load denormalized. Load denormalized.sh, Mike.sh. There we go. Down here, up arrow, run. Okay, and now things seem to be working like they were before. So we're in a good spot. And now we have just a single command right here that we're trying to run, so that's good. Actually, though, it's kind of two commands, though, isn't it? Because we have this sh and then the load denormalized.sh. What happens if I try to take away that sh right there so that we really do have just one command, up arrow, rerun that? Now we get this load denormalized.sh command not found. Anytime you're referencing commands in the current folder, the / in front of it can resolve that sometimes. Permission denied. Oh no, what do? I give myself permission. Chmod all plus execute. We'll be a little bit picky here. Only give me permission, not everybody. User plus execute. Load underscore denormalized.sh like that. And now up arrow, bash, run that. And now things are working. And we do in fact have a one-line command here to load tweets from a zip file into the database. Based on this, I can use my GNU parallel command that we've talked about previously. And what I'm going to do is I'm going to let's see, echo. Let's see what happens when I do echo $files like this. And I will comment out these things up here so they don't run. I just want to see what's going to happen here. So let's see if I can pipe this possibly into my GNU parallel. Save that down here, up arrow, rerun. You can see that everything right here is being outputted onto a single line instead of multiple lines. GNU parallel expects things as multiple lines. And so let's put them in double quotation marks so we don't ignore all that white space. Up arrow, rerun. Now everything is on its own individual line. And so I can pipe that into the parallel command. And the thing that I want to parallelize is this /load normalized.sh like that. Come down here, up arrow, rerun. We're getting this dumb citation message. Maybe I will so that I don't have to deal with that. Let's add that citation flag like it's asking me to. Up arrow, rerun. Okay, it's making me yeah, so what it's doing is well, it's not important. Well, okay, yes, sure, why not? What it's doing is they really, really want you to cite their parallel program if you are a professor writing a paper, getting it published somewhere. And so they're making it kind of obnoxious to get that message away, and you have to create like a hidden file on your system saying that your settings are guaranteeing that you have acknowledged that you must cite it, blah, 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 blah. And so I don't want to do that right now. It's not important. So we'll just suck it up, deal with this stupid warning message. And there we go. And all 10 of these happening in parallel very fast. We're still not actually displaying what the runtime is here, though, of these operations. So Shift-I, take me to the beginning. Time this whole thing down here, up arrow, rerun. And and now we're going down to 4 seconds is our runtime. So that's pretty good. Well, I mean, so originally one was what, like 15 seconds or something. So we didn't get the full 10 times speed up here on the denormalized insertion because it turns out actually that a lot of the slowdown is just for like IO related reasons. And it's just not possible to get any faster with our hard drive set up on the Lambda server. So for the denormalized, you won't get the full 10 times speed up, but for the normalized and the normalized batch, you should get like at least 9 times speed up. And so this is a full credit answer to the denormalized. Doing the normalized without the batch, there's not, you shouldn't run into any, what are they? Deadlock issues. When you do the parallelism, you should be able to write a similar command like this, stick it into the normalized here, and everything should just work, get you your 10 times speed up. But because it's not batched, it's still really, really, really slow, and so it's still not good enough. And so we have to batch insert in parallel. And this is where the fun of the assignment is going to come in. I'm going to switch my screen over here. So we've talked about, we're looking back at the README file for the homework now. We've talked about the denormalized data. We've written our POSIX script right here. I guess we haven't called the check answers right here. You'll notice that I have done a whole lot of inserts right here. Let's just do a real quick Docker compose exec pgd normalized dot slash check answers. There we go. And everything should fail because there's just way too many tweets in here. I've been inserting tweets nonstop in here. And so I guess it's taking a long time to run these complex queries. I'm just gonna press Control C and these things. I know they're gonna fail. In order to actually check your work, recall that you'll need to bring down your compose down, bring down your database, go down. And then that's not enough because we're storing the information on volumes. The container has been wiped. Any changes to the container go away when we bring them down, but the database is not stored in the container. It's stored in the volume that the container references, and the volumes are persistent. And so we also have to do the Docker volume prune command to free that up. And you can see actually I have quite a bit of information stored in there, like almost 4 gigabytes at this point. And then Docker goes up. You don't have to build it after deleting volumes, just bring it back up and then reinsert, then rerun the check answers, and then it should work. But make sure that your parallel check answers are working, not just the sequential check answers. Okay, so PG denormalized batch, that's what we're looking for. So the normalized data unbatched, again, should just work. You'll just have to write the code in the shell script like I did for the denormalized, and the normalized batch, this is the one that's going to be fun. So the key problem here is that you're going to run into deadlocks. These deadlocks are going to raise all sorts of Python errors, and there's many ways that you can resolve these. The sort of naive way to do it is to, so the naive method is to catch all the exceptions that are being generated by the deadlocks, and then if something failed to insert, just try reinserting it. But it turns out if you do that, not only will you not get parallel speedup, you'll actually get what's called parallel slowdown, that everything will be in a constant state of deadlock and you'll never even actually get things inserted. So it will just be in a constant state of programs aborting and before the data actually gets inserted from the deadlocks. So what we need to do is we need to actually remove the deadlocks, prevent deadlocks from happening. I've got a little outline of what to do here in order to do that. So the deadlocks are caused by the unique constraints in the database in this case. We've seen that there's a handful of other ways that can cause deadlocks as well. Unique constraints, though, are the most common cause of deadlocks in database systems. And anytime you're responsible for a large database and you think you might have to do bulk inserts or have many processes working on the database, the unique constraints should be something that scare you a little bit because they should be a deadlock concern for you. Maybe scare is too strong of a word. We want those unique constraints for data integrity issues. We care about our data. We want it to be correct. The unique constraint ensures that it's correct, but the downside of the unique constraint is that we get these deadlocks. Things will happen slower if you're not careful. In this case, the only way to resolve the problem is to totally eliminate the unique constraints. And doing that is going to be a little bit tricky. The most tricky part is going to be this get id URLs function. Let's come back over here, and I want to remind us what that function looks like. Load tweets underscore batch.py get id URLs. And right now, the way our database is set up is that we have a separate URLs table. Let's go ahead and load up the schema too. So tab E services / PG underscore normalized underscore batch / schema.sql. Let's find the URLs table right here. And everywhere in the database, when we're referencing a URL, instead of referencing the URL directly, referencing its text, we're referencing an integer that represents the URL, a unique ID of the URL. Technically, this is the normalized representation of this information. It prevents us from needing to store the same text, the same URL, many, many thousands of times potentially in the database. So it can save some disk space for us. In this case, URLs aren't too long. It turns out that actually URLs are limited in size to 256 characters. So they can't be that long. Sorry, I take that back. Its domain names are limited in size to 256 characters. URLs, due to a Microsoft limitation in Internet Explorer, are in practice limited to about 2048 characters. A cool web browser like Firefox could handle larger URLs, but nobody uses those in practice because a large portion of the internet would not be able to view them, and they would just be really big. Yeah, so most URLs not very large, so not saving too much disk space. If those like documents, then it would be more important to have the denormalized representation. Sorry, it'd be more important to have the normalized representation for large things to save more disk space. In this case, though, the normalized representation is what is slowing us down with this unique constraint on the text, because when we're inserting things, they're going to be having conflicts on generating the URL IDs over here. And so this function right here is going to be causing a lot of the deadlock issues when it's doing the insertions. In order to fix this, I've got the outline here of what you'll have to do, but you're going to totally denormalize the URLs table, the representation of URLs. Delete the URLs table, and then everywhere where a table was referencing id URLs, change it to represent the actual URL directly in text. So it'll use up a little bit more disk space this way, but we're not going to have the deadlocks as a result. Foreign key constraints, turns out you can only have a foreign key constraint if you have a corresponding unique constraint. And so any of the foreign key constraints that represent id URLs, you'll also have to delete those as well. And that makes sense because there's not going to be a URLs table anywhere. So this will be a handful of work to do both in the SQL schema, and then after you've done that in the SQL schema, again, deleting this table, deleting all references to id URLs everywhere. After you've done that, you'll have to modify the Python code as well to get rid of this get id URLs function. It's not meaningful anymore because you're never going to use the id of URLs. And so everywhere where you were previously calling this function, you will now have to just reference the text of the URL directly. There's more that you'll have to do in order to prevent all of the deadlocks from happening, but a good programmer will not try to do all of this at once. Instead, they will just do one thing at a time, get the URLs denormalized, and then you will check using your sequential insertion that everything is still working with your test cases. That way you can verify that you don't have any bugs related to the URL denormalization. After you have done the URL denormalization, there are a handful of other unique constraints you'll have to handle as well. And you'll have to do, well, you're not going to have to do any denormalization related to these other unique constraints, but you will have to do some stuff. And I'm not going to tell you what that stuff is. So you will have to figure it out yourself. You will get lots of painful Python error messages here. Happy to help you deal with those painful Python error messages when you encounter them. But I want you to actually encounter them for yourself first, and then we can talk about what's going on. After you do all of those things, you will have a somewhat normalized, somewhat denormalized representation of the data. This would actually be my preferred representation of the data for a system like this. And then the parallel insertion will all happen correctly. Again, don't forget on your submission to fill out this table with all of your runtimes. That's it for this assignment. Yeah, the next assignment, just um, to give you a heads up, you'll be using this same code, but now instead of working with just 100,000 tweets, you'll be working with 100 million tweets. I don't know, lots of data, lots of tweets. I think it's going to be about 20 gigabytes of tweets, whatever that works out to in terms of numbers, and you will need the insertion tools to happen very fast so that we can test your query tools. We'll be talking about indexes next in class and how to use indexes to make SQL select queries happen faster. So, and that will be your next assignment. That is it for this assignment. Good luck.